Greetings and welcome to a new video about analog filter design. In this example, we will discuss the bandstop filter design, where we use the parallel combination of a high-pass filter and a low-pass filter. It will be a wide band filter circuit, and we will use the Butterworth response for our realization. Of course, we'll see everything step by step and verify these in SPICE simulations. Before we jump to our design example, I will first briefly discuss the bandstop filter configuration. For that, we can use the parallel configuration of a high-pass filter and a low-pass filter, and then required cutoff frequency and a passband gain can be designed using these two filters. Now the diagram is shown here. You see here the low-pass and the high-pass. They are now in parallel, as we can see here. So we have the input and the output, and then the total effect will be then a bandstop filter as shown here. And this is the Bode plot in more detail. You see here the low-pass action, and then it comes up because of this high-pass filter circuit, and then again it comes back to this value which we call the passband gain. You see here the lower cutoff and the upper cutoff frequency, and also the center frequency in this situation. Now, if the cutoff frequencies are too close to each other, so if this is, for example, let's say 1 kHz and this is 2 kHz, which is very close to each other, then it might be that the final design have a shift in the cutoff frequencies compared to the individual low-pass and high-pass cutoff frequencies. So it can be, of course, difficult, and also the mid-band gain can shift. There you need to use a different topology and different algorithm to calculate that. Now, at some point, the task can be really difficult, and also a lot of trial and error needs to be done, and that is also not really handy. And for that, we need to use the GAFE algorithm. I have discussed that also in a separate video. But this time, we will use a wide band design, so there we don't need to discuss that GAFE algorithm in this case. Okay, let's look at our design example. We have now here an objective: design a Butterworth response, an active bandstop filter. The specifications are shown here. We like to have a maximum passband ripple, which is shown here at 3.01 dB, which is exactly at the cutoff. So at this gain, we require our cutoff frequency. The minimum attenuation we want is 20 dB, and the effective passband gain should be 0 dB or 1. The lower cutoff frequency is 200 Hz, and the upper cutoff frequency is 2 kHz. So you see here there is a difference of 1 decade, so 10 times larger. So this is pretty wide band, you can say. If this, for example, was a 200 and 400 Hz or 200 and 300, it is almost impossible to design this by just making two circuits, a high pass and low pass, in parallel. In addition, we see here the lower stop band frequency, 500 Hz, and also the upper stop band frequency of 1 kHz. At these two frequencies, we need to have an attenuation at least 20 dB. That's actually the meaning of these specifications. Okay, now we have discussed already briefly what we need to do. So we need to set the parallel combination of the low pass and high pass filter, and also add them up together. So first we start with the high pass filter design. That is the part where you have the cutoff for this region. Now we start first with epsilon P and epsilon S related to that A max and A minimum. In this case, it's 3.01 dB, so that is almost 1, so 0.9999. And the other one for A minimum, which is 20, that will result here in this 9.9499. Now taking these together, now the filter order for the high pass part using the epsilon values we just calculated, and also the upper cutoff frequency, this one, 2000, and the part here, the upper stop band frequency. Now when you substitute the values, you get here almost 3.3. Of course, we need to go to the integer value, so we need to have an NS4 for our high-pass filter circuit. Now the circuit realization will be a two-stage situation. We have a cascade of a two-pole Sallen-Key high-pass filter, another two-pole Sallen-Key high-pass filter. And that's actually shown here. You see here the two stages, here the stage 1 and stage 2. And the gain configuration for this operational amplifier is 1. So you see here the buffer, so you will get 0 dB gain. Now, the component values for this design, you start first with calculating the resistors by selecting the capacitors here. So the 4 capacitors we see here, we select them as, for example, 10 nanofarads. And then you calculate your scaling factor, like so, R which is a parameter or a scaling factor we will use, is equal to 1 over the omega ch, which is our upper cutoff frequency in the radians per second, times the c we have here selected. Now this is of course 2 pi times the upper cutoff frequency. So that will result here in 2 pi times 2000 from the specification times 10 to the power minus 8, which is 10 nanofarads. And that will result in this value. This is an important value, which is then a scaling factor in order to calculate this R1 up to R4. And for that, we need to bring up our Butterworth response table. And we need, since we design a high-pass filter, we need to look at the row here with the ratios of the resistors and our scaling factor R. Now, this is the row we need to use. This is the fourth order. You see also here the two-pole and a two-pole section and its associated parameters. Now, from the table, we see here the first stage is using 1.082 and a 0.9241. That's actually the first one. And the second one is this. You see here again rewritten such that we have the R1 and R2 directly. Now we know R from our scaling factor. Now we know the parameter scale factor from a table. So we can calculate that. So the first one is this. The second resistor is this one. In similar form for R3 and R4, you can calculate it using again the table and our scaling factor as shown here. Now the design is actually completed for our high-pass filter circuit. Now looking at the low-pass filter circuit, that is the part where you have this decrease in the actual bandstop filter. Just again looking at the maximum and the minimum, so the A max and A minimum, these are the exact same values as for the high-pass filter, so we can go here a little bit faster. But the formula is a little bit different because it's the exact same actually in the format, but you need to use the stop band frequency for the lower part and the cutoff frequency for the lower part. That's actually where you need these two parameters here. So when you substitute this, you get here 2.5 approximately, and we need to go for an integer, so that means we need to have an N3. So the low pass filter should have a third order. Circuit realization will be a 3-pole Sallen-Key low pass filter circuit because this is just a third order, and that is shown here. You see here the 3 resistors are equal to each other, all of them, and we have 3 capacitors we need to calculate. Here we need to do the component selection like setting the resistors here, in this case for example 1 kilo ohm. We can also go for a different value. And then the scaling factor is really this capital letter C, which is a 1 over this lower cutoff frequency times the R we have selected here. And I may now substitute here the 2 pi times the lower cutoff frequency times the resistor here. You see the full details here, you will get this value. And this is again an important value because we need to use that in this Butterworth response for this row, which is our third row. Now, since we design a low pass filter, we need to look at these capacitor ratios. So that means 3.547, etc., 46, etc., and those 3 parameters we need to use. So you see here the C1 is indeed this times our scaling factor C. The next one is this value 1.3920 times our scaling factor C, and etc. Now when you now do the calculations here, you get here these capacitor values for C1, C2, and C3. Now the design for the low pass filter is also completed. Now we're getting closer. Now we can actually set up our complete band stop filter circuit, and that is now in full detail shown here. You see here now this high pass 4th order circuit, and here the low pass, the 3rd order circuit. In addition, in order to add them together, you cannot just say wire them together and then add them up and then make the output node. You need to add them up using a summing amplifier. In this case, I have used an inverting summing amplifier, and those 3 resistors then are taking exactly equal to each other such that you have an exact addition without any weighting. So this is a summing amplifier, and these are the results for the resistors and the capacitors, and these are all 1 kilo ohm resistors as selected. You can also take 5 kilo ohm, all of them. It doesn't matter for most practical purposes. Okay, now the next one is about the simulation circuit in the Tina TI Spice. You see here again exact same circuit. Now in the Tina TI Spice simulator drone, you see here again the high pass part, 4th order, low pass part, 3rd order, and our summing amplifier. Okay. Now our design should be verified. Now we go to the Bode plot in the simulation result. You see here the gain and our frequency in the log scale and our gain here. The blue line is our gain curve. You see here the DC gain is indeed 0 dB, and also the high frequency gain is 0 dB, as we want, because that's the effective passband gain, so that is checked. The lower cutoff frequency is indeed 200 Hz. You see here that the gain drops by 3.01 dB, which is the lower cutoff frequency, as we wanted. And again, the gain is minus 3.01 dB, again dropping by the same amount at 2 kHz, which is also what we wanted, so that's the upper cutoff frequency. Now the gain at 500 Hz is here minus 24.4 dB approximately, but this is of course more than 20 dB we wanted minimum, so that's also perfect. And at 1 kHz, we see that the gain is minus 25.26 dB, again more than the minimum required 20 dB. In addition, we see here the notch, which is spiking down. That happens at almost 750 Hz, which is our center frequency, which is not the geometric mean of these two values, which should be the case, for example, for most cases. Again, because these are, again, maybe not too wide to each other. That's why we have a different value here for the notch frequency. But that was also not a design criteria here, because that was only looking at the lower and the upper cutoff frequencies and the lower and the upper stop band frequencies. Looking at the design and our results here from the Bode plot, we can say design is completed and we have achieved our goal. Alright, it was our example considering the Butterworth response active band stop filter using the parallel combination of the low pass and high pass circuit. We have to use the Sallen-Key filter circuits and calculate our component values using the Butterworth response table. If you have any questions, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.